So there's three situations. We've only looked at two situations. You've got a simple linear factor. Okay, now this right here you might want to label. We call the x minus 2, we call that a simple linear factor. And it's a linear. Okay, that's why it's x minus 2. That's linear, so that's a simple linear factor. And then this one right here we call a repeated linear factor like that. So you have to set this up in a certain way. So the first thing when you're working with partial fraction decomposition, the purpose of that is to break this one fraction into, two or more fractions with those denominators. So the first thing you got to do is you got to get this set up correctly. So let's go ahead and let's just write down what we're working with. I always want to just write that expression down. And then we got to break this up a certain way. You want to kind of spread your work out because you're going to get rid of fractions. Ultimately, you're going to set up a system of equations. Okay? So what we do is the first one is linear. If you just have a linear factor, you just go a over x minus 2. That's all you do. And your job is to figure out what a is. Now you want to put a little room there. Then you want to go b over x minus 3. Don't do x minus 3 to the second. Do x minus 3. Then you want to spread out your work a little bit. Then you want to go c over x minus 3 to the second like that. When you have a repeated factor, you have to do it like that. If that was x minus 3 to the third, well then you would have to go to plus d x minus 3 to the third and so forth. Okay, so that's the first thing you got to be solid on. Does that make sense? Okay, all right. Now what we need to do is let's get rid of the fraction. So we're going to multiply everything by x minus 2 times x minus 3 squared. Okay, so I'm going to go ahead and do that to each term. Okay, with a little practice, you can process this part in your head. I'm going to write every little step out as I'm doing those. That kind of keeps me from making any stupid mistakes. Okay, so let's kind of get that written out like that. And then what we want to do is we want to just cancel whatever cancels. You want to go ahead and do that, and then we'll see where we're at with all this mess here. So that cancels everything out there. Okay, so that's going to leave me with x squared minus x. Okay, let's see, the next one, the x minus 2's mark out, so that's going to leave me with a times x minus 3 to the second. And the next one, one of the x minus 3's crosses out. Okay, just one of them though. So that'll be plus b, then that'll be x minus 2 times x minus 3 like that. Okay, then the next one, that crosses out, so that will leave you with plus c times x minus 2 like that. Okay, everybody good with that? Okay, now what I'm going to do is I'm going to go ahead and multiply this out. I'm going to show you a couple of ways to do this system of equations. So we have to ultimately find a, b, and c in this problem. So what I'm going to go ahead and do is I'm going to kind of use this little trick that I showed you. And what we're going to do is we're going to start with just kind of letting x be something that'll make this easy. Okay? Well, what would happen if we let x equal 3? Wouldn't that cross this whole thing out? And it would cross this whole thing out, right? So see, that is an easy way to find one letter. So if we let x equal 3, what's going to happen? And you just kind of do this in your head. That's going to mark that off. That's going to mark that off. So what you're going to be left with then is you'll be left with x squared minus x is equal to c times x minus 2. And then if you just replace x with 3, you'll be able to easily find what c is. I use x minus 3 because it helps me get to that stage. Okay, so you want to take advantage of it. So now we'd have 3 to the second minus 3 equals c times 3 minus 2. So that's 9 minus 3, which is 6. And then that would be c. Look at that, we got c equals 6. Okay, so we already got one variable. Does that make sense? Why I chose c equals 3, or x equals 3. Okay, what's another good thing to let x equal? 2, good, okay. And the reason we want x to be equal to 2 is because it'll cancel something else out. Okay, so I'm going to take advantage of that idea also. With a little practice, you can do this in your head. So if x is 2, that'll mark that whole thing out. It'll mark that whole thing out. So what you're going to be left with then is x squared minus x is equal to a times x minus 3 to the second. Okay, everybody with me on that? Okay, now plug in 2 for x and solve this equation. So you're going to have 2 to the second minus 2 equals a times 2 minus 3 to the second. That should allow us to figure out what a is then. Okay, so then what we can do on this then is that would be 4 minus 2, so that's 2. This is a. Now see, this whole thing right here, that thing right there looks like that's just 1 because that's negative 1 squared. So we have a is equal to 2 like that. So all we got to do now is we got to find b. Okay, so there's a couple of ways that you can go about doing this now. If you want to find what b is, you could multiply this out and try to get just one equation with a, b, and c in it. So I'm going to go ahead and do it that way. The other thing you could do is you could go back and replace in this equation the a and b with, or the a and c with what their values are. So what I'm going to go ahead and do is I'm going to work with this equation right here. We want to focus on that, and we're just kind of multiply this out and regroup, and we need to find one more equation where we can find b. Okay. All right, so watch how I do this carefully. Okay, it's not that hard. It's just algebra. So I'm going to do this piece right here. So that's going to be a. I'm going to square out the x minus 3. So that's x squared minus 6x plus 9. Okay, I'm going to multiply out the x minus 2x minus 3. I can do that in my head. That's x squared minus 5x plus 6. And then I'm going to multiply out the last one. I'll just bring that down kind of like that then. Okay? Now what I want to do is you want to see if you can do this in your head. I mean, if it's necessary for you to multiply all that stuff out and regroup, then do that. But it's kind of nice to do this in your head also. So what I'm going to do is I'm going to look at all these x squareds and I'm just going to put those together. Okay, so I've got, if I do that, I would have x squared times a plus b. And I'm just factoring that x squared out of that piece right there. Okay, then I could put together anything that has an x in it, like that. So if I do that, I'm going to have plus, it looks like I'm going to have, if I take an x out of that, okay, what I'm going to end up having is I'll have a negative 6a minus 5b, and then plus c like that. Okay, and then the last thing I'm going to do is I'm going to put together the numbers. So like I have a 9, I have a 6, and I have a negative 2. And I'm just kind of multiplying that out. So I have like a 9a, then I have like a 6b, then I've got a 2c like that. So let me pause there for a minute and just kind of, and make sure you follow that because I'm trying to get you to save a little work on your paper. So all I'm kind of doing is just, okay, that's x squared a plus b. This is minus 6a minus 5b, and then c, and then I've taken the x out. You guys see what I'm doing on that? Okay, if you can't do that in your head, just take the time to multiply all that stuff out and then regroup everything like that. Okay? Now, if you look at what we did last time, let's see if we caught on to this. If you look at this equation now, what does a plus b have to be equal to? 1. It has to match that coefficient, right? If that's x squared, that's got to be 1, so it matches. What does this thing got to be? Negative 1, right? Okay. What does this thing got to be? 0, because there's not a constant term there. So what you're doing is you're matching the coefficients of the powers of x. Does that make sense to everybody? Okay, so let's write down our system. We don't have to solve the system, though, because we already found one variable. So again, this part right here, a plus b has to be equal to that 1 right there. So let's write down that equation. That's a plus b is equal to 1. Okay. Then the second equation, even though we don't need it, I'm going to go ahead and just have you write it down. That thing has to match that coefficient. Okay, so that would be negative 6a minus 5b plus c equals negative 1. And then the last thing would be this thing has to be 0 because there's not a constant term there. So we'd have 9a plus 6b minus 2c is equal to 0. Now see, we've already got a and b. All we got to do is we got to find c now. So what I'm going to do on this one is it doesn't matter which equation you deal with. These all have an a, b, and c in it. So let's go to this equation. We already know A is 2. We already know C is 6. So that should allow us to figure out what B is. So I'm just going to have negative 6 times 2 minus 5B plus 6 equals negative 1. So that's negative 12 plus 6 is negative 6. Minus 5B equals negative 1, like that. Then I can add 6 to both sides, like that. So that looks like that gives negative 5B equals 5. So I get B is equal to negative 1. Okay, like that. Okay, and you can end up with fractions on these problems. It's kind of nice if you don't have to have that. But we got everything that we need now. Okay? So that's algebra. It's usually students do well with this. Just be careful and make sure you don't make any arithmetic mistakes. And once you get that, you're going to have integrals that are not too hard to solve and put together then. Okay, you guys got any question about all that stuff I did? Yes?
So like, would C only equal 6 when x is 3? Or,
So,
or like, is that just a way to make it easier to find the answer? Like, will A only equal 2 if x equals 2?
Yeah, well, you're solving a system of equations, so there's one unique solution to it. Okay.
So you just find an A solution for that part of it, and then make a system out of it and solve the whole thing?
Yeah, and when you have a system of equations, or anytime you have a system of equations, you generally have 3 possibilities. Either it intersects in some place and gets one answer, you get no answer, or you might get infinite answers. Now, because of the crossing on this, now these are systems in three unknowns, which if you graphed it, it's 3-dimensional now, but it's going to cross in one place. So these problems, you're generally going to get one answer. Yes, one answer. Yeah, so once you find, the first variable, I mean, it's always going to match and give you one solution on these things, okay? Okay, now let's go put this together now. So what we're doing is we're doing the integral of x squared minus x over x minus 2 times x minus 3 to the second dx. So let's put this together. Now I'm going to kind of highlight, this is what we're doing. We now know what a, b, and c are, so we figured out that a was 2, we figured out b was negative 1, and c was 6. So when we write the integral, we're just going to break it up into 3 integrals. So we're going to have the integral of 2 over x minus 2 dx for the first one. Okay, the second integral is up here, so that's going to be the integral of negative 1 over x minus 3 dx. And then the last integral is this one. That's going to be integral of 6 over x minus 3 squared dx. Okay, so see, that's the whole point of that problem, is that once you do the partial fraction decomposition, now you can do your integrals pretty easily. Okay? Okay, everybody okay so far? Students usually, I find, do pretty good with this, because the algebra is kind of tedious and takes a while to do, but it's not hard. So what we're going to do is we're going to go ahead and just do these integrals. So really, what you're doing is these first 2 you can do in your head. You're just bringing the 2 out. So that's 2, okay? Can you tell me what the value of that integral is? You want to do that in your head, just boom, boom. ln x minus 2, right? Okay? All right, you don't have to do a U-substitution on that. That's just ln absolute value x minus 2. That's what that is. You generally get lots of natural logarithm integrals on this. Okay, can you tell me what the answer to the next one is? ln of absolute value x minus 3. Good. Now, can you have that minus 1? That constant's coming out of the integral, so that would be minus ln x minus 3 like that. Okay? So see, the integration's easy once you get it put together. Now, this last one is different. That is not a natural logarithm one. That is, you got to do something with U-substitution because you have a second power there. So it's not an ln. Okay? It may end up being an ln, but you got to go through a U-substitution integral when you do this. So what I'm going to do just is let's focus on just this integral right here. And I'm going to just bring the 6 out like that so that we have 6 times the integral of 1 over x minus 3 squared dx like that. Okay? Now what we're going to do on this one is we're going to do a U-substitution. So I'm going to let u be x minus 3. Okay, that's going to be that piece right there. And then du is just going to be dx. Okay, so what I'm going to have with this is a real simple U-substitution integral like this. Okay, so what I end up having on this one is I end up having 6 times the integral of du over u to the second like that. Okay, everybody with me on that? Okay, how do you integrate something like that? It's not a logarithm. What do? Bring that u to the second up top, right? So when you do that, you're going to have 6 integral of u to the negative 2 du. Then that's a power rule integral, right? So what you're going to have with this then is you're going to have 6 u to the negative 1 over negative 1 like that. So that will just be negative 6 over u like that. And then your u value was x minus 3, so that thing plugs back in there to give you negative 6 over x minus 3 the second. So that's the value of that last integral. So we had to kind of go to the side of a paper and do u substitution. So now we end up with the last piece of this integral is minus 6 over x minus 3 the second plus c.
It shouldn't be to the second anymore. It should just be x minus 3.
What's that?
It shouldn't be to the second.
Oh, why not a second? Why did I put a second there? That's clearly a u there. Okay, I'll let work and then I do something stupid like that. I don't know why I do that. I'll just say it's 8 in the morning. That's why I did that. Okay, if that's okay with you. Okay, there we go. So that's your answer. Okay. All right. So does everybody understand the integrals? Once I got it broken up, how you do the integrals. Okay. So see, what you'll generally have on this is you'll generally have natural logarithm integrals on these things, because you're going to have, like, the denominator is going to have x plus something or x minus something. And if you have a power, like a second or third power, which we'll have, then that's usually u substitution is what's going on there. Okay. So that would be the final answer to that problem. It's a lot of work. It's not too hard. We're getting close to the point, probably by the end of next week, we'll be done with everything we're going to learn about integrals in this class. So it'll be kind of when you get back from spring break, it'd be time to start doing the gateway test. And we always have a couple of partial fractions integrals on the gateway test. So you want to be able to know how to do that. Okay. All right. Any questions before I move on? Okay. All right. So let's go to the next thing here. Now this one is a little bit different situation here. And this is the third situation that we need to look at. This is what we call an irreducible quadratic. So this is another situation that you have to look at when you're dealing with partial fractions. Okay. So what I want to show you on this is, first of all, what we mean by an irreducible quadratic factor. Just to give you an example, you might write this down. I just want to remind you of this. So if you had x squared plus 4, now that's a quadratic expression. If you set that equal to 0, wouldn't you get complex numbers? Yeah, I mean, if you solved an equation like that, what would you do? You would move the 4 to the other side. You would take the square root of both sides. You would have x equals plus or minus 2i, right? You get imaginary numbers when you do that. So the idea is x squared plus 4 does not factor. Okay, anytime you have a trinomial, some quadratic expression that doesn't factor, then we call that an irreducible quadratic factor. So x squared plus 4 gives imaginary number solutions because it doesn't factor. It doesn't factor through real numbers. So what you're going to look at is sometimes your factors, maybe one of them or maybe both of them or all of them, are irreducible. So the general setup goes like this. Instead of just putting a over the factor, b over the factor like we've been doing, you got to do ax plus b over the factor. So that's how you got to get that set up. So you got to recognize when you have this setup, and then you got to put this together right. Okay? All right, does that make sense what I mean by irreducible quadratic factor first? Okay, something like x squared plus 9, or anything that doesn't factor. Okay, if it doesn't factor through real numbers, it's going to be like that. Okay, so let's set this up. So you want to write this down. This is x squared plus x plus 2 over x plus 1 times x squared plus 1. So you want to get that kind of set up. Okay, now this thing right here, we call that a simple linear factor. So we have a simple linear right here. X squared plus 1, does that factor any further? No, that is an irreducible quadratic factor. So if you have x squared and a quadratic expression and it does not factor any further, that's irreducible quadratic factor is what that is. Okay? So when you set this up, you got to set it up like this. So the first thing you do is you just put a over the linear factor. You do that. Okay? Then you want to have a gap here like this. Then what you put on top of the irreducible is the form ax plus b. Now you already used a, so go to bx plus c like that then. Okay, that's the setup. So that's different now. Okay, everybody with me on that? Okay, anytime you got a quadratic factor that's irreducible, you got to have like a bx plus c, that kind of format like that. Now the rest of it's the same. We have to set up our system of equations. So what you're going to do is you need to multiply everything by both factors because you want everything, the denominators, to cross out. So I'm going to go ahead and put this factor in each position like this. And then we'll kind of carefully cancel everything out, and then we'll see what kind of system of equations we have, because that's the idea. So that would be the setup with the linear and an irreducible quadratic. Okay, so I'm going to write down what I have now. So it looks like everything, of course, cancels there. So we got that. So that I'm just going to write down as x squared plus x plus 2. Don't factor that x squared plus x plus 2. You want it like that. You want it multiplied out like that. Okay, go to the next one. That crosses out. So that's going to leave me with a times x to the second plus 1. Over here, those cancel. So that will leave me with bx plus c times x plus 1 like that then. And then what I'm going to do is I'm going to multiply all this out. Now, there's a couple of things you could do on this. I'm going to set up a system of equations on this. One thing that you might think about doing is if you let x be -1, well, that would cross this whole thing out, and then that would allow you to find a. Okay, now I'm going to do that just kind of at the side of the paper, but I still am going to need to do my system of equations anyway. Okay, so let's do that to begin with. Let's let x be -1. Okay, is everybody with me that that would cancel that whole mess out right there? Right? Okay, so what you'd have left, if x was equal to -1, then what you'd be left with is you would have x squared plus x plus 2 is equal to a times x squared plus 1. And now, since we're letting x be -1, that would be an easy way to figure out what a is in the problem. Okay, take advantage of that. So now what I'm going to have here is -1 squared minus 1 plus 2 is equal to a times, and then this will be -1 squared plus 1. Be very careful with all your arithmetic and everything when you do this. So this is going to be 1 minus 1 is 0 plus 2 is 2. That looks like that's a times 2. I'm just doing the basic arithmetic in my head. So it looks like a is going to be equal to 1 is what I should get on that then. Okay, so I've got a equals 1. So we got that taken care of. All right? Has everybody got that? And understand why I let it be -1? Look for that, okay, because it'll help you get those things a little quicker. Now, I still got to find b and c. There isn't anything else I could let x do that would cancel stuff out, okay? There's just nothing else. So what I need to do is just go through and multiply all this stuff out and then get my system put together. But I do have a, so that'll make that a little simpler. So I'm going to multiply that out. So that's going to be ax to the second plus a, just doing a distributive property. Okay, then what I'm going to do here is I'm going to do just multiply that out. I'm going to do a distributive property and FOIL this. So that's going to be bx squared. Outside term is plus bx. Inside term is plus cx. And the last term is plus c, like that. Okay, so let's multiply everything out. Now we want to kind of get together that system. So what I'm going to do is you want to group together your x squareds. You want to group together your x's. And you want to group together those things like that. Okay, the constants like that. So what you're going to have is you're going to have x to the second plus x plus 2. And then just put these together. So I'm going to factor an x squared out, and that's going to be x squared times a plus b. And that'll take care of those two things. Okay, then I'm going to factor out the x here, so that'll be plus x, and that'll be b plus c. And then that leaves me with a plus c, like that. Okay? Everybody okay with that? Okay? So now, once you kind of get everything grouped, then you're kind of looking at kind of the same situation. Your system's pretty easy from here. Tell me what a plus b has to be equal to. 1, because it has to match that. What does b plus c have to be equal to? 1. What does a plus c have to be equal to? 2. So you have a coefficient of each term like that. Everybody got that? Okay, so that'll be our system. And then we need to solve the system to figure out what the other two variables are, but we already have a, so we're going to have a plus b. That piece right there is going to be equal to 1, like that. Okay, then we got the second piece, b plus c, has to be equal to that coefficient, which is 1. Okay, so I'm going to write that down, b plus c equals 1. And then finally, the a plus c has to be equal to 2. Okay, so that is my system of equations. You get one unique answer to these things typically. So we already know what a is. We already know a is 1. So we might as well just take the first equation and replace a with 1. So we have 1 plus b equals 1. So what's b? 0. Okay, so we got b is equal to 0 in this problem. Okay, now we need to find c. So we could go to this second equation, which is b plus c equals 1. Well, we just figured out b is 0, so we have 0 plus c equals 1, so we have c equals 1, okay? And one thing about a lot of these problems, I mean, you're doing all this work, you can actually, most of the time, this is an example of a problem, you can tell you're right. I mean, if you look at this, a plus b is 1, okay? Look at this, a is 1, b is 0. 1 plus 0 is 1, right? Then you got b plus c is 1, look at that. 0 plus 1 is 1. Then you have a and c is 2. 1 plus 1 is 2. You see what I'm doing on that? A lot of times your systems are easy enough that you can really quickly tell you're right. Okay? Sometimes you can't. Okay, so here's what we do now. We're now ready to put together our integral. So I'm going to write down the integral we're working on is x squared plus x plus 2 all over x plus 1 times x squared plus 1 dx, like that. And again, the integral is these pieces right there. Those are the two pieces of your partial fraction decomposition that I've highlighted in yellow there. Okay, so it's going to go like this. We're going to set up two integrals, essentially. So a was 1, so we're going to have the integral of 1 over x plus 1 dx there. Okay, that'll take care of that. And then the second integral, let's see, b was 0. And let's see, c was 1. So what's the numerator going to be? It's going to be 1, right? You have 0x plus 1. So that's going to be 1 over x squared plus 1 times dx, like that then. So that's the integral that we've done. Now this is just a different situation with the irreducible quadratic. Now, the integrals are very easy to do on these. So once you got through all that mess, it's easy to write your answer, okay? All right, can you tell me what the value of that integral is? ln x plus 1. Be sure you have that in absolute value. So we have ln of x plus 1, like that. Okay, how about this next one? We know it. In theory, you've learned it before. What is it? Inverse tangent. That's inverse tangent, okay? You have to kind of go back, like if you go back into Calc 1, if you do the derivative of the inverse tangent of x, that is 1 over x squared plus 1. That's a derivative rule. So that one is the inverse tangent of x, and then you have the plus c like that, okay? Now we've seen that inverse tangent quite a bit in here. Then the idea with that one is sometimes we've seen like x squared plus 4 and stuff like that, where we did that 1 over a arctangent of x over a, so it's the same idea. Okay, how's that look? Okay, yeah.
So after you found, when you set x equals to -1 to find a, could you let b, or did you let x be equal to 0, and then you would have like a b term, and since you already know a, could you solve for c that way?
Yeah, I think so. If you're saying if you go back, I think to this point right here, right? Yeah, if you let x be 0, you would end up, if you did that, you would have a plus c times 1. You'd still have 2 variables in there.
Right.
And, you know, you could work with that.
Yeah, I guess then, because if we had already found what a was.
Right, yes, exactly. So if you replaced a with 1 there, yeah, you're fine. You could do it that way. So there's several different ways you can do that. You can just always do a system of equations. You can try to eliminate a variable by picking, like what I did or what you're thinking, 0. That would work fine if you did that. Ultimately, you're going to have to, when you get 2 variables, you're going to have to go back to one of these equations in your system anyway. So that's typically what I do, is just set the system up and then find anything I can before I solve the system. That's my approach, okay? Okay, everybody okay? All right, let's see. This problem that I did before, I think I wanted to mention this on this. I kind of forgot this. One thing that you want to do on this is on page 5, so you might want to back up there. I wasn't paying attention to this. I mean, that's an okay answer. It really is. But one thing that you can do, and we talked about that last time, is you can combine logarithms. So I just want to go ahead and do that, have you finish that. So that would be ln x minus 2 to the second minus ln of x minus 3 minus 6 over x minus 3 plus c. Okay, now how do you put together these 2 logarithms? You do a fraction, right? Okay, anytime you have a difference of logs, you can put them into a log of a fraction. So that would go like this. You could write this as ln of x minus 2 to the second all over x minus 3 like that, minus 6 over x minus 3 plus c like that. Now, one thing that we did, we talked about this a little bit before, that's an even exponent. So if that's an even exponent, no matter what x is, you're going to get a positive number unless x is equal to 2. So you can actually just replace that with a parenthesis. Okay, you don't necessarily have to do that, but I just want to remind you that that's an even exponent, so that could be written that way. However, the absolute value on this has to stay the same. It has to stay absolute value. How come? It's an odd exponent. Anytime you take a negative number to an odd power, what happens? You get a negative, and you can't take logarithms of negative numbers. So that's a little detail of that problem that you have to pay attention to. I think generally on your homework on My Math Lab, they generally are going to have you put your logs together, so don't forget how to do that. Okay? All right. So let's move to, let's see, I think I want to do a couple of applications, although I'm not going to do the integrals. I'm just going to use this as an opportunity to review a couple of things. So I've kind of gone through all of the basic cases that there are. I think I'm going to do one more partial fractions. This one just has a different factoring issue that maybe you haven't seen in a long time. So let's work with this example. And see, in this particular problem, the denominator is not factored. So if you're given an expression where the denominator is not factored, you want to do that, okay? So let's focus on how to factor this. Do you guys know how to factor this from your background? Grouping. It's got 4 terms. That is a factor by grouping problem. A lot of times students haven't seen that in a while. So I want to remind you how you do that. So what I'm going to do is we're going to group together the first pair and the last pair. We take out common factors. So when I do this, the common factor of this first parenthesis is what? X squared. Then you'd be left with x minus 1. Okay, the second factor, what's that? 4. So you'd have 4 times x minus 1 like that, right? Now what you do on this is the common factor, see now what you have is you have a common factor of x minus 1, so you pull that out. Okay, you just take that x minus 1 and you pull it out, and then if you take that out, what's left is x squared plus 4. Okay, so the factoring on that, of course, is just x minus 1 times x squared plus 4. Okay, does that look familiar? Well, I hope so. Okay, because it shows up some. Okay. Okay, we teach factor by grouping for different reasons. That does show up a little bit. So our integral, what it really is it's going to be x squared over x minus 1 times x plus 4 dx. Okay, so we got to get this set up with partial fractions, okay? All right, what do you call x minus 1? What's the vocabulary? What do you call that factor? Simple. Okay, that's simple linear. Okay, how about the x squared plus 4? That's an irreducible quadratic. Okay, like that. So you have to set this up kind of like I did the last problem. Really, it's the same idea as the last problem. Okay, that doesn't factor because it's got a plus sign. Now don't do this. I still see students in Calculus 2 who want to do this. Okay, drives me crazy. Well, I understand, but you don't go plus 2 minus 2. Is everybody on top of that? I hope so, okay, because it doesn't check, right? Okay, that's an irreducible. I see students do that in all levels, so don't do that. Don't make that mistake. Okay, now what we're going to do is we have x squared over x minus 1, x squared plus 4, and we're going to set this up like this. So what you do is the linear one, what do you do on the linear one? You go a over x minus 1. That's how you handle that. Okay, now you go to the irreducible. What goes on top of the irreducible? Bx plus c. Okay, that has a structure to it. So that's bx plus c. Okay, so you have to do that like that. All right, now the process is the same idea. So we're going to multiply everything by those two factors because we're trying to get rid of those two factors. Okay, like that. All right, and then we'll kind of write what we have and see what kind of system of equations that we're going to have on this one to solve it then. Okay. Okay, so now that I want to get everything crossed out. So, of course, everything crosses out there, leaving you a x squared. In this situation, we're going to have a times x to the second plus 4. And then over here, the situation is going to be bx plus c times x minus 1 like that. Okay, so I've done that enough. Everybody probably has that down okay. Now, what I'm going to do with this is I'm going to go ahead and multiply it out and get the system, and then we can kind of get that done here. So we have x squared equals ax squared plus 4a. I'm going to FOIL this out, so that's going to be bx squared minus bx plus cx minus c like that. You can bypass this if you can handle all this in your head. So this is x squared. I'm going to put together the squared terms and write that as x squared times a plus b. Then I'll take care of that. Then I'm going to put together the x terms. It doesn't matter what order you put those in either. I'm going to factor out a x, and I'll just write that as negative b plus c when you factor that out. And last, that will leave us with 4a minus c like that. All right, everybody good with that? Okay. Now let's put our system together and kind of get that thing put together. Then we're going to have to kind of get that done and get to our integral on here. Okay, so in this particular problem, tell me what a plus b has to be equal to. 1, right? It matches that coefficient. So you're going to have a plus b is equal to 1. Okay? How about negative b plus c? What does that equal to? 0. There isn't an x over there, right? So that is negative b plus c equals 0. Okay? And the last one, what does it have to be equal to? 0 also. There's not a constant term on the left side there, so you're going to have 4a minus c is equal to 0 like that. Okay? Now you can solve this system in different ways. This one's a pretty easy system to solve. You could also go back to this equation right here, and you could let x equal 1. If you want to start the problem that way by letting x equal 1, then that would be a real easy way to find a. And that's the way I'm going to do it, because it's just simpler to me. So let's do let x equal 1 right there, and that would cross that whole thing out, right? So that would leave you with this thing, okay? And if I do that, I'm just going to replace x with 1. So I have 1 to the second, I have a, and then I have 1 to the second plus 4 is going to be like that then, okay? So that's going to be 1 is equal to a times 5. So that looks like what we're going to get on that is a fraction, which is perfectly fine. We get a equals 1/5. Okay? Now I did a little bit more of that in my head. You'll be able to do that okay. That letting x be 1 crosses this whole thing out, and then it gives you that simple equation to solve. Okay? All right. Now let's see what we got from here. Well, we can go to this top equation here. So what we have on that, or we could go to the bottom, it doesn't matter. We have a plus b is 1. So if a is 1/5, we would have 1/5 plus b is equal to 1. Now that's going to be a simple equation we can solve. So that's going to be b equals 1 minus 1/5. If you get a common denominator for the 1, you would have 5/5 minus 1/5. So that's going to be b is equal to 4/5. Okay? All right, everybody okay with that? Okay? All right, fractions. You got to deal with the fractions when they show up. Now I'm going to go to this equation and see, I now know what b is. So b is 4/5. So this equation is going to give negative 4/5 plus c equals 0. So c is positive 4/5. Okay, so we got all that stuff taken care of. So that's the system. That would be, to me, probably the simplest way to put that system together is like that. Okay, any questions? And I've done that enough times. That's about the last time I'm going to do the technique of partial fractions in the section. We're going to do some applications, but just mainly setting stuff up. Okay, so now we're going to set up our integral. So we're working on the integral of x squared over x minus 1 times x squared plus 4 dx. And we want to set this up, and our partial fraction decomposition is right here. Okay, that's what we're setting up as that. Okay, we found that a was 1/5. We found b was 4/5. And we found c was also 4/5. So we're just going to write all that stuff down and see kind of what we have now. So it looks like we're going to have 1/5 like this. A is 1/5, I think. So that's going to be 1/5 over x minus 1. And that's an integral, dx. So we do that. Okay, then the second integral looks like it's going to be 4/5 x. Okay, plus 4/5 all over x squared plus 4 dx like that. So then that's going to end up being the integral that we're going to work out. Okay. Any questions so far? Okay. Now, it looks like what we have to do on this is you're probably going to end up having one little U-substitution integral. The first one you can do in your head. This integral right here, what's the answer to that integral in your head? 1/5 natural logarithm of x minus 1. So that takes care of that. Okay? That happens all the time on these problems. Okay, the next one kind of has an arctangent look to it, doesn't it? Kind of, okay. So I've got that. Now, one thing that you got to do on this one is you got to, if you're working on this integral, let's think about the strategies we've learned how to do there. If you just did U substitution and let u equal x squared plus 4, when you did the derivative, you would struggle with matching in the numerator. So any suggestions about how I do this integral? Split it. Exactly. Let's split it. So let's just kind of focus totally on this second integral here and see what we got, and we'll put this all together. So let's look at the integral of 4/5 x over x squared plus 4 dx, and then split it into a second integral, and let's look at 4/5 over x squared plus 4 times dx like that down. Okay? So this one right here looks like a good U substitution integral. So I'm just going to pull that out. I could have just saved a step and left that out. I'm going to write that as x dx x squared plus 4. Does that look like a U substitution integral? Yeah, what are you going to let u be equal to? The bottom. Okay, so let's do that. So we're going to let u be x squared plus 4. Okay. du is going to be 2x times dx like that. Okay, since we're trying to match that with an x dx, let's divide by 2 to get 1/2 du is equal to x times dx like that. So here's your u. There is your 1/2 du. So that's a pretty straightforward U substitution integral then. Okay, so what I'm going to have left with this is I'm going to have 4/5. I'm going to have the integral of 1/2 du over u like that. Okay, now what you can do with this one is you can bring the half out. So if you multiply 4/5 times the constant 1/2, you're going to have 4/10, which does reduce. And then what's the value of that integral going to be? ln of u, right? Okay, that's 1 over u, integral of 1 over u is ln. So that's going to be ln of absolute value of u. But u was equal to x squared plus 4. So I plug it back in, then I'll reduce the fraction on that, and I'm going to get 2/5 ln of x squared plus 4. Okay, so far we have that, and we have that. And we got one more integral to do, then we got to write our whole answer together. Okay, so it's a little bit more complicated on this one. You couldn't do the integrals in your head. Okay, all right, everybody good? Okay, now we got to focus on this last integral. Does that have a structure that you're familiar with? We've seen that before, right? What kind of logarithm? What kind of integral is that? That's an arctangent integral, right? Okay, so what you're going to do with this is you're going to bring the 4/5 out, and then you're going to have the integral of 1 over x squared. And this is the one, since 4 is a perfect square, you write that like this, and then we had a formula for that. The formula that we've looked at several times is if you have 1 over x squared plus a squared dx, the formula, how did that go? 1 over a inverse tangent of x over a. That's a formula that we've used a lot in this class. That shows up pretty often. So that means that what this integral is going to be is 4/5 times 1 over a. Now see, a is the number that's squared to get a 4. So that's going to be 1 over 2. Then that's going to be the inverse tangent of x over a. So that's x over 2 like that. Okay? So then that we can put that together. You can multiply out those fractions if you want to. So 4 over 2 is 2, so that leaves you a 2/5. So now we're going to put all this mess together and write the right answer. Okay, so the answer to this problem, we have this thing right here, 1/5 ln x minus 1. We have this thing right here, which is plus 2/5 natural logarithm x squared plus 4. And then we have this thing right here, which looks like that is plus 2/5 and then that would be the inverse tangent x over 2 plus c. Okay, and you can write the answer that way. You can also put the logarithm together on that one and do that as well. Okay, so I'm going to put the logarithm together also, but that's one way to write the answer. Okay, that's probably the most complicated problem I've done on this, just because the integrals are harder. And you aren't going to run into anything that's much more than that. Okay, when you put this together, it's going to go like this. When you put the logarithms together, you can do this in your head if you feel comfortable with this. I'm going to do this in my head, and you can tell me if you're comfortable with this. I'm going to write ln x minus 1 to the 1/5 times x squared plus 4 to the 2/5. And then this is plus 2/5 inverse tangent x over 2 plus c. That would be the best way to write the final answer. Everybody with me on how I did that logarithm? Because I did that in my head. I just brought the exponents up, and a sum of logs can be written as the log of the product. That's the property of logs like that. Okay? All right. Any questions about that? Okay. What do you think of partial fractions? You have any opinion yet? It's not too bad. Okay. So you got those three situations. You set that up. You got to do systems of equations. Okay, now what I want to do next here is a couple of applications. Now I'm not going to do the integral because I just don't want to take the time to do that. All I'm going to show you on this is revisit applications we've already learned how to do. And what I want to show you on this is these kind of integrals seem to look like a partial fraction integral. Okay, so it's kind of good to review some of the basic things that we've done on this. Okay, what I'm going to do on this one, I'm going to get the calculator out. You probably should just get your calculator out and follow along the graph on this one, and let's do that. This is a good one to just look at, visually see what's happening on the graph. So I'm going to put in this function. One thing that you want to be super careful about is be sure that that denominator is in parentheses. So I'm going to have x squared. I'm not even going to bother factoring it because I'm not going to work the integral out anyway. I'm just going to set it up. Okay, so I want to get that put together, and we're going to find the region. We're going to look at the area of the region that's bounded by that curve and the x-axis, and we're also going to look between -2 and 2. Okay, so let's get our window set up, and what I'm going to have you do is, since we're interested in -2 to 2 on x, it's always good to go out a little bit further. So I'm going to go -3 to 3, scale of 1. And the y-axis on this one, let's do something like, let's start with the same thing. I just want to have a pretty good viewing window, so let's kind of try that approach right there. I'll slide the window over there so you can kind of see what I've done there if you need to. Okay. All right, now I'm ready to graph. So I'm going to do a graph, and we'll see if this is a pretty good picture of this thing. So that's the curve right there, and we're going to be looking at the region that's bounded by the x-axis in this. So that looks to me like a pretty good graph. So I'm going to slide that over and just kind of put this. You can make yourself a very simple sketch on your notes. It doesn't have to be perfect, but something kind of like that. What I'm going to do is label, this is a 3, that's a 3, -3, and so forth like that. Okay? So doing the graphing will kind of help you visualize what's going on in the problem. So what we're trying to do, and we've learned how to do this, is you're looking at x equals -2, and you're also looking at x equals 2, like that, and you're interested in the area between the x-axis and the curve, so you're interested really in that shaded region right there. That's what you're trying to find, okay? So what we're going to do on this one is just set the integral up. I'm not going to do the integral, but I am going to do the integral numerically on the calculator, just to remind you how to do that. Okay, so let's see if we remember how to set this up. We haven't done this in a long time. So how does the integral go on this one? If you have an area between two curves, what do you generally do? Like the curve on top, right, minus the curve on bottom. Okay, we're going to do a dx integral on this, so you might make yourself a note that we're just doing top curve minus bottom curve. And we're going to do a dx integral because we want to integrate from -3 to 3. Everything's set up nicely. We're not rotating or anything. We're just doing an area. So that would go like this. The top curve is the x-axis. Well, the x-axis is y equals 0, right? Okay, so that top curve is y equals 0. And that bottom curve is what I gave you, which is 10 over x squared minus 2x minus 24 dx. And then we're going to integrate that from -2 to 2 like that. Okay? So what I'm going to do on this one is you are going to have a negative here. So when you do 0 minus that, that is really going to be a negative. So the way I would write the integral out is like this. I'd have negative integral, -2 to 2. You can even take the 10 out if you want to. Doesn't really make that much difference. I'm just going to leave it in because I'm going to do this mostly numerically anyway. So anyway, that would be the integral that you would do. Okay? Does that make sense? Does that look like something you've remembered how to do in this class? Okay? Now, does that look like a partial fractions integral? Why is it partial fractions? Because it's a factorable trinomial, right? So if you have a factorable trinomial, you would factor and you would do partial fractions to get a precise answer on that. Now, I'm not going to do that because I feel like I've done enough partial fractions. I've done a bunch of them. So let's just take our calculator and let's put this in. Now, the only thing you got to do on this now, our integral has a -10 in it. So I'm just going to insert a negative in there. So I really need to work out this integral right here. And I'm just going to do this numerically. So if I graph that, that negative is going to change that. It reflects it. Now, since I'm doing this numerically, all I do on this is I just go second calc, I go down to option 7, then I put in the limits of integration. So the, whoops, did I miss that? I think I missed it. Let me try that again. So option 7, lower limit is -2 on the integral, upper limit's 2. It'll shade that in, and then it should give us an approximate answer on this when we get that then. Okay? Now that's a different integral. See, what I'm doing is I'm graphing the integral that's working out the problem like that. So if I work out the value of that integral, then you're going to get this right here. Now, if you went through on this one, and if you worked out that integral by partial fractions and everything, you should end up getting about around 1.79 like that and everything. Okay, so I'm just saying if you worked out this thing by partial fractions, this integral, you should get that. Something similar to that. Okay? All right? Yes?
Would it be negative?
Well, what happens on this one, now your area below, when you're doing this area right here, you should get a negative region there. Okay? So if you integrated from here to here, you should get a negative value. Now, I don't know if I put the...
You did put it in the equation, but would your final answer be negative?
Okay, if you worked out this particular integral right here, you would end up getting some sort of a negative answer to this integral right here. Right. Okay, because see, you have that negative there.
Right.
Okay, but when you're doing this area right here, that's below the x-axis. The reason this is happening is because of when you're doing this integral, you're really looking at that region there, okay? But then what happens is that negative changes it back to a negative, like that, okay? So if you worked that out by partial fractions, that would be the answer that you would end up getting. Okay, all right. So I just wanted to remind you how to set that up. Let's look at this next one and just kind of take the same approach and use this just kind of as an opportunity to review a couple of things here. Okay, so what we're going to do on this one is now we're going to revolve around a line. So let's go through and let's put in the graph of 1 over x plus 2. Okay, right there. Let's do that. So I'm going to get that put in. Now let's see, for a window on this one, I'm going to do something like, we are revolving around the line x equals, I think we're revolving around x equals -1. So let's do kind of a similar window. I think I'm just going to start by going to maybe, I think I'm going to go like -4 to 4. And I'm going to leave the y's the way they are. I'm just going to see if that's a pretty good picture of the graph, because we're going to be rotating this not around the y-axis, but around the line x equals -1. So let me see what this looks like and see if that will work okay for a fairly good graph. Okay, I think it will. Now what I'm going to do is just take this to, I'm going to change my window. For x minimum, I'm just going to do -1, because that's really what I'm interested in, is rotating around the line x equals -1. So I think if we do this window, that should give us a pretty good view on here. Then I'm going to just kind of do the graph and have you sketch a graph on here then. Okay, so this is all we need so that we have a pretty good picture here. Now what we're going to do is we're going to set up an integral. We're not going to solve the integral. We're just going to set it up here. Okay, so that's your window. So if you want to do that on your calculator, you can certainly do that. And that's what you would roughly be set up with, is that then. Okay, so we haven't done this in a while, so I'm just kind of using this as a review primarily. So what we're doing is we're taking this region, and we're going to be bounded by y equals 0. Y equals 0 is just the x-axis. And then you have x equals 0. You're also bounded by x equals 0, which is this piece right here. And then you're revolving this around the line x equals -1. Okay, like that. So that's x equals -1. And then what we're doing on this one is we're basically taking that region. And we also have x equals 3, so we need to go up to x equals 3. Like that. And then what we're really doing is taking this region right here. We're taking this line. This is what we're doing, is this piece right here. We're looking at that region right there from 0 to 3, and we're revolving that thing around the line x equals -1. So that's what we're doing on that. So kind of imagine in your mind what's happening, and we'll kind of talk about what method we want to use on this. So, okay, what's happening is it's saying that you're going from 0 to 3, but you're revolving that around that. So wouldn't you have a little gap there? Yeah, okay, you'd have like kind of a, some sort of a shape going over like that. But then you would have that gap there. You could do washer, you could do shell. I think I'll do shell on this, because shell's just as easy to me to just do it this way. So what I'm going to do on this, if we do shell, the idea is you want to figure out mainly what the shell radius is and what the shell height is. Those are kind of the key things on that. So let's think about how this one would work with the shell method. And if I do this, when you do an integral with a shell, it goes like this. This is the one where you have 2 pi, and then in this case, I kind of have my radius there. Okay, then what you have is times the height, like that essentially is what you have. So you have 2 pi r, you're doing cylinders, and that 2 pi r is basically giving you that circumference around that cylinder. Then you're doing the height, and then that gives you that cylinder. So the cylinder kind of goes like this. One thing that to me is kind of helpful on a problem like this is, since we're rotating around this, I'm going to draw just kind of a little picture of a cylinder on here. Let's see if that kind of helps you reason this out. So if I did a cylinder, kind of a circle around like that, you're going to have something roughly kind of going like that. And when you rotate that around, the radius on here is going to be from that point right there to wherever you are there. Okay, that's going to be like your radius right there. Okay, so you got to get that put together. And then the height is going to be whatever the function value is. So when you have that height is just going to be the value of the function, like that. Okay, the thing you got to be so careful on this problem is if you're going to do the shell method, the radius, you got to be careful about that. The radius is not just x on this problem. What you have to do on this is the radius is going to be the distance from some point on here to that line -1. Okay, and this is the place where I think a lot of students would slip up on. So let me explain this. Okay, let's say that you're over here. Let's just say that your radius is right there. Now your radius is not the x value, because that would just be that little slice there. That's your radius. It's all the way from there to there. So what you're doing is the radius is the distance between that point and that point. How do you find the distance between two numbers anyway? You subtract, right? So if you just go x minus -1, then you give what the radius is. So it's always that way. If you're way out here, the radius is going to be there, so it's going to be that x value minus -1. That's giving you a distance. Does that make any sense? That's a big deal on this problem. The radius is a distance between two things. So what you're going to do on this radius is you're doing this. Okay, I'm going to just kind of draw a little picture. That's radius right there. So you would have x, you would have -1. So the radius is the distance from x to -1. So we just go like that. So that radius is going to be x plus 1 like that then. Okay, that's the value of that radius. So in this shell formula, the radius is going to be x plus 1. Okay, so when we put together our integral, we're going to have the integral of 2 pi times x plus 1. Okay, that's that 2 pi r part of the shell formula. Okay, now what's the height in this problem? That's easy. That's the function value, right? That's how tall the function is. So that right there, that is going to just be the function value. So that's going to be 1 over x plus 2, like that. And then what we're going to do on this with the integration on this is we end up going from 0 to 3. So we're interested in this to there, okay? Since we're rotating that from 0 to 3 around that line, then we're going to integrate from 0 to 3 like that. And then that would be how the setup of the shell on that one then. Okay, you could also do this problem with the washer method pretty well too, because of that gap. Okay, so what you'd do, and I'm not going to work this out, but you would take out the 2 pi, so you would have 2 pi integral from 0 to 3 of x plus 1 over x plus 2 dx. Now we've learned how to do that same integral in different ways. You could do that by partial fractions. That's a nice partial fractions integral. So that's the reason I wanted to go over that, is just to show you that when you're doing certain types of functions, and if you're doing a shell or a disk or washer method, you might come up with a partial fractions type of integral. Okay, you guys follow that? The radius is the tricky part up to me on that one. You're just doing a distance between two numbers. That's why I'm subtracting. Okay? All right. Any questions? Okay. Okay, now let's see. Next page, I'm going to do just a summary, I think. So this just kind of gives you a summary, and we're not going to do the partial fraction. We're just going to do a couple of setups, and then I want to do there's a couple of more integrals that I want to do that are a little bit different ideas. So this one, let's just set up the partial fraction. Let's make sure that we have this under control. We're not going to integrate. We're just going to set up how you would do that. What would you have to do first if you were going to do partial fractions on this one? You'd have to factor, right? So you always see if that factors. That does factor. That would factor as x and x to get the x squared, of course, 3 and 3 to get the 9, with 2 minus signs like that. So what you would end up having is you would have 2 over x times x minus 3 to the second. Now it's real important that you write it that way, okay? So let's see if we remember the terminology or not. What kind of factor do we call x? That's a simple linear. There's a certain way you set that up. How about the next one? That's what we call a repeated, right? We call that a repeated linear factor. So it goes like that. That's repeated linear. Okay, so when you set this up, it goes like this. You're going to just say A over, then you would have X plus, then you would do B over what? X minus 3, then what? There you go. You have to set up those repeateds that way. Okay, I'm not going to solve that because I've done a bunch of that. I just want to review the setup of these things. Okay, all right. Okay, the next one. What do you call x to the third?
Is that going to be c over x minus 3?
What's that?
Is it going to be c over x minus 3 squared?
Yep. Yeah, because what you do if it's a repeated, you have to go like x minus 3 squared, x minus 3 to the cube, and so forth until you get to that highest power. You got to kind of count out the power. Okay, so this one you have a repeated linear. Okay, what do you call the x squared plus 1? That's irreducible quadratic, right? Because it does not factor. So we have a certain way that you set this up then. So the way you would set this up is like this. You would say a over x, right? Then what? It's repeated, so what do you do? B over x squared, then what? Okay, everybody with me there? Okay, what do you do for the quadratic one? What goes on top? dx plus e. There you go. I'm not going to work that out. I'm just saying that's how you would set up the partial fractions. So that's a pretty important part of the section, is to be able to set that up regardless of what those factors are. Okay? All right. Any questions? Everybody got that okay? Okay. All right. Now let's do, let's see. I had a couple other integrals of just a few different types here. This one can be done with partial fractions. It doesn't look like a partial fractions integral at all, though. I mean, it's got like a 1 plus e to the x in it. So what I'm going to do on this one is I'm going to show you that this is sort of a partial fractions integral kind of in disguise. But what we're going to do is use substitution. So the first thing that I'm going to do on this is I kind of apply, this one's kind of tricky. I'm going to apply a little trick on this. So I'm going to let u be e to the x. Now let me explain why I'm doing that. If I do that, then my integral would have the structure something over 1 plus u. Is that a linear factor? Yeah, that's a simple linear factor. So I'm trying to transform this into something that I can use partial fractions on. That's my thought process on this. Well, here's the weird thing about this. du would be e to the x dx. That's not what we're left over with, okay? Every now and then, when you're doing some of these problems, you have to do some sort of a little trick to this. So let me show you kind of what I'm going to work with on there. So let's just write this integral down again. So I'm going to write this as 1 over 1 plus e to the x like this. Now, this is just a really tricky thing. I mean, this is something, sometimes you get into integrals and you have to be clever. So what I'm going to do on this is, and we've done stuff like this before, is I'm going to multiply both the top and the bottom by e to the x. And there's a reason why I'm doing that. If I go to U-Substitution, see my du is e to the x dx, right? So that's kind of my thought process is, man, it would be nice if I could introduce that e to the x dx, and I've done that. Okay, does that make any sense? I think you'll see how this works out once I get to the point on there, but that's my thought process. So let u be e to the x because I want it to be a partial fractions integral. Now what I'm going to do on this is we're going to work this out a little bit further, and when I do this now, the u substitution is going to go like this. Okay, that thing right there is going to be a u. That thing's also u because that's what I let that be equal to. But then this thing right here is going to be the du part, like that. And let's see if we can handle that integral. Hey, we got everything accounted for. That's the number one thing in u substitution. So when we have that, we're going to have the denominator. What's the denominator going to be? It's going to be 1 plus u times u. Okay, like that. Now, the numerator, e to the x dx, that's just going to be du. Okay? Okay, tell me if that makes sense. Okay, does that look like a partial fractions integral? Yeah, how come? Because it's got two linear factors. It's got 1 plus u and it's got u. That is a partial fractions integral. So this thing at first glance doesn't look like partial fractions, but it can be done that way. Okay? All right, so let's go ahead and let's work this one out like this then. And you have to work this out like this. So that in the numerator, what you're doing is you're working out 1 over 1 plus u times u. And yeah, we're going to do partial fractions on this. We're going to do the same idea. So if I do this, I'm going to have a over that linear factor plus b over that linear factor like that. Okay, so we're going to work out the u integral first, then we'll resubstitute in the u to get our answer like that. Okay, so same idea. So this one we're going to multiply by 1 plus u times u, and 1 plus u times u like that. Okay, and let's just write down what we have left. Okay, we'll, I think, have a pretty simple system of equations on this. So that cancels all that out. That's going to leave you just a 1 there. Over here, that leaves a times u, like that. Okay, and then over here, that cancels that out, and that leaves a b times 1 plus u, like that. Okay, well, let's see. Our system is actually very easy on this. We just have 1 equals a u plus b times u, like that. Okay, then I'm going to put together things. We're used to having x as the variable, but it still doesn't matter. So I'm going to have 1 is equal to u times a plus b. Those two things right there get put together. And then we'll have just the leftover b like that. Okay, everybody with me okay? Okay, now let's see if now we have a different variable. It's still the same idea. Let's see if you know what I'm talking about with this then. Right? What does a plus b have to be equal to in this problem? 0. There's not a something times u, right? What does b have to be equal to? 1. How do you know? That's a constant. That's a constant. So your system is going to be a plus b is 0. That's nothing there. And then b equals 1. That's a super, super easy system of equations. So that's how that goes. Okay? So again, you want to match it up like this. Technically, this is a 0u is understood to be there, if you want to think of it that way. So a plus b is equal to 0, like that. And then we have, of course, b is equal to that constant 1, like that. Okay, so we got b is equal to 1. And then if you take your top one, you can do that in your head. That's just a plus 1 equals 0. So what's a? A is -1, like that. Okay? All right, now what we're going to do now is we're going to put together this partial fraction right here. So what we're doing right now is we're doing the integral of du over 1 plus u times u. Okay, so we split it up in the partial fractions this way. A was -1, b was 1, like that. So you're going to end up with the integral of -1 over 1 plus u du plus 1, the integral of 1 over u du, like that. Okay, that's going to be a real simple thing to have there then. Okay, all right, everybody okay? All right, tell me what this integral is. -ln 1 plus u, absolute value. How about the next one? ln absolute value u plus c, like that. Okay, now all you got to do on this now is you got to remember the u. Now if you go back to where we were working with this u substitution, the u substitution was e to the x. So we're going to put that in like that, and then we'll kind of put this together and get our answer put together. So we're going to have -ln 1 plus e to the x plus ln of absolute value of e to the x plus c, like that. Okay, and that's an answer. I'm going to put the logarithms together, and that would be the answer of the integral. Okay, so when we have this, you can do this all in your head if you want to. I'm going to move that negative up so that I get ln 1 plus e to the x to the -1. Okay, and then this is just going to be ln of e to the x. So how do you put these ln's together on this problem? Just add. It's a product, okay? So the sum of logs becomes the product. So we just say ln 1 plus e to the x to the negative 1 times e to the x plus c. And then the other thing I'd probably do on this is I'd probably write it this way. Since that's a negative exponent, it would make a lot of sense that you could just do ln of e to the x over 1 plus e to the x to the first power, like that. And then since they're both to the first power, actually the ideal way to write the answer to this problem would be like this. ln of e to the x over 1 plus e to the x plus c. Okay, that would be a beautiful way to write the answer. Okay, so I think that's a cool integral. How about you? It's kind of different, okay? It's got a U-substitution that turned us into a partial fractions idea there, okay? And that one actually is not that hard to check. I mean, if you did the derivative of this answer and worked with it a little bit, it'd take you back to the beginning. It's not that bad because it's got e to the x in it, okay?
So how do we swap the trick?
Okay, that's a great question, okay? Now that takes a little bit of experience to see that, but, you know, the idea, if you just sort of go back to, you know, what we've learned, I mean, you wouldn't really be able to get much of anywhere. You could try parts. Parts may or may not work. But the idea is, if you're going to do a U substitution, this is what I'm thinking. If that's a U, then I would end up having 1 plus U. Now, what's beneficial about 1 plus U is that's a simple linear factor. So that makes me think partial fractions is a possibility. Okay? Now the idea, the problem is though, if u is e to the x, then what's du? E to the x dx. And you don't have that, right? So since you don't have that, you got to be sneaky. Sometimes you can be sneaky on these problems. So what I did was I said, well, let's just multiply that by e to the x and that by e to the x. And by doing that, everything would be taken care of, see. This thing right here, isn't that just du? Okay, that's why I multiply it by the x, so I would be able to account for that du. And then that's a u, and that's a u, and then that's a partial fractions integral. So one thing that you can kind of look for sometimes is, and the fact that it's an e to the x is what makes that possible. If that was something else, it'd be pretty hard to, it probably wouldn't work this way. But e to the x, since its derivative is the same, allows you to do a partial fractions on that. Does that make sense? Okay, this is kind of a little different situation there, and you'll run into little ideas like that sometimes as you're working things out. Okay, so let's work this last one out. I'm going to go and finish that one, and then we'll do our break here. Little bit different kind of an integral. This is one more partial fractions. The idea with this one is the numerator. The thing that you got to recognize on this one, we've certainly seen this before, is yeah, you're going to factor this and everything, but what do you notice about the top and bottom? There's something I want you to see on this. The exponents. Okay, the degree of the top is what? 3. The degree of the bottom is what? 2. The degree of the top is bigger than the bottom. What did we typically do on integrals like this? Well, remember we did division. Now, because that power is higher, you wouldn't want to just go through and factor that and try to do it by partial fractions until you've divided that out, okay? So the first thing we're going to do is, for that reason, we're going to set up a long division problem. So we're going to have z squared plus z minus 6, and then under that symbol, we're going to put all the numerators. So that's 2z to the third plus z to the second minus 6z plus 7, like that. Okay? Then we'll kind of see what we have there. Does everybody understand why I'm doing division? That's your job, is you have to understand, okay, what the situation is and what leads us to that. Okay? Well, let's do the long division now. And some of you had a little trouble when you were learning long division. The first thing you do is you divide these two terms. You do this in your head. I'm going to kind of write down what I'm doing. So if I divide those two things, of course, what do I get? I get 2z, right? Okay, that's step 1, is to do the division and record it. Step 2, what you're doing is 2z times z squared plus z minus 6. I'm writing that down for the benefit. Some of you never learned how to do long division this way because you're from another country, okay, where they don't teach it this way. Not everybody teaches division this way. So what I'm going to do is 2z times z squared is plus 2z to the third. 2z times z is plus 2z to the second. 2z times negative 6 is negative 12z, like that. Okay, so we get that. Step 3, what do you typically do? You subtract now. Okay, now you can subtract in your head like this. I usually teach students to kind of do it this way, is when you subtract, you're really changing the signs and adding. I think you may be less likely to make a mistake if you do that, but you don't have to do that. The idea is that minus that is nothing, so that cancels. Then this is really z squared minus 2z squared, so that's going to be negative 1z squared. And then see, this one is really negative 6z minus negative 12z, because you're subtracting, so it's really plus 12z, so that's going to be a plus 6z, like that. Okay? And then the other thing you got to do is the step 4 of this division algorithm is to bring down the 7 like that. Okay? Then we do have to do one more phase through the long division like that. Okay, everybody with me on that? Okay, I got to do it again. I got to start over again. So what I end up doing here is basically this. I'm going to just erase those two things and just kind of show you what I'm doing here again. Okay, so what I do now is I look at this and this. So I'm doing negative 1z to the second over z to the second. So of course that's negative 1. So you record the negative 1 there. Then it's all the same. You're going to multiply negative 1 times z squared plus z minus 6. Just do that in your head. So that will be negative 1z to the second minus z. And then negative 1 times negative 6 is plus 6. And then step 3 is you subtract again like that. Okay, you can subtract in your head, or you can try this approach if you like. Change the signs and add is what I do. Okay, so what you're going to have is that's going to cancel. That's 6z plus z, so that's 7z now. And then this is 7 minus 6, so that's plus 1 like that. Okay? Now, I'm going to ask you a question on this now. This is kind of important. Okay, how do I know I'm done? Because now, see, the power of that is lower than that. Because see, if you did z over z squared, you would end up having a negative exponent, right? Okay? So we're done with the division, so what we need to do is we need to write this like this. Okay? So when we do this, it's going to go like this. This integral now changes into this. So what we have, like we learned before, is this is going to be 2z minus 1 plus, and then the remainder is going to be 7z plus 1 all over z to the second plus z minus 6 like that. So that's the integral we're going to do, and that's more manageable than the one that we're going to do. Okay, now let's kind of think about this a little bit. Okay, we're obviously on the sections with partial fractions, so I think this has something to do with this. So you would be able to integrate that with ease, right? 2z to the second over 2 minus z, right? That's super easy integral. But this one looks like a partial fraction situation here. So let's go ahead and let's write this down, kind of split it up into two integrals. So we're going to do this integral, which we can do in our head, like that. Okay, now the second one, you're going to have the integral of 7z plus 1 all over, and then you need to factor that denominator, and that does factor, so that is z plus 3 and z minus 2 is what you would have on that then, times dz like that. Okay, now does this second one, doesn't that look like a partial fractions integral? Okay, that's the whole purpose of this. It's sort of a partial fractions problem in disguise. So yeah, we're going to do this one last time. This is the last time I do partial fractions. I know I've done it a lot, but it's a real important technique, and it's important to see the different situations that show up. So we're going to work with this integral. We already know this integral is going to give 2z to the second over 2 minus z. Okay, so that gives you that piece of the integral right there. Okay, now let's go ahead and let's work with the partial fractions, we're going to focus totally on this guy right here. Okay, so that's going to give 7z plus 1 over z plus 3 times z minus 2 equals, and these are both linear factors, so how's it go? A over z plus 3 plus b over z minus 2, like that. Okay, so I'm going to do this real quick. See what we get here. So I'm going to get rid of my fractions. Okay, and then we'll kind of get our system of equations built when we do this then. Okay. All right, let's see what we got here. That cancels. That cancels. That cancels. So it looks like what you're left with is a 7z plus 1 equals a times z minus 2 plus b times z plus 3, like that. Okay, now we're going to set up our system. Now we could also, on this one, if you want to, let's just see if we can figure it out by this method. Okay, what's a good thing to set z equal to? Let's start with 2. If z is 2, that whole thing right there crosses out. That thing right there, right? Okay, so what you'd be left with is 7 times 2 plus 1 on that side is equal to b times 2 plus 3. Like that. So I think we can avoid doing a system on this problem. So it's kind of nice. So that is 14 plus 1 is 15. That's b times 5. So if we divide by 5, we're going to get b is equal to 3, like that. Okay, so that's what we should get. Okay? All right, what's another good thing to let z be equal to in this problem? Negative 3. Okay, so let's let it be negative 3, so it'll cancel that out. Okay, so when we do this piece right here, in your mind, you just know if z is negative 3, that wipes out, and you're going to be left with 7 times z, which is negative 3, plus 1, equals a times negative 3 minus 2, like that. So that looks like negative 21 plus 1 is negative 20. That's equal to a times negative 5. Now if I divide that out, I got a is equal to 4, like that. Okay? All right? So now let's put the integral together. Okay, remember we're working on this thing right here. That's our integral that we're working on right here. So what we're going to end up having is the integral of 7z plus 1 over z plus 3 times z minus 2, whoops, z minus 2 dz is going to be this. Okay, if you look at the split up, it goes right there, what I just highlighted. So you would have a is 4, b was 3. Okay, so we're going to have basically the integral of, this got broken up into 4 over z plus 3 dz plus the integral of 3 over z minus 2 dz, like that. Okay? All right, I'm kind of whipping through that because I've done that a ton there. Okay, so now I'm ready to put the whole thing together. Okay, now you can't forget about stuff. Sometimes when you do messy problems like this, you got to remember we had that thing right there. That was a part of our answer right there. So that thing is a part of our answer. We would have z squared minus z. That came from when we did the long division. Now the rest of it's easy. What's the value of that integral? Well, 4 natural logarithm. Okay, that's another logarithm integral. So you're going to have plus natural logarithm z plus 3. This one right here, another natural logarithm. That's going to be 3 ln z minus 2 plus c, like that. Okay, that's your value of your integral right there. And then what you could do is you could just put the logarithms together. So we're going to have z squared minus z plus ln. Since this is a sum, you would have ln of z plus 3, bring the 3 up, and then that would be times z minus 2 to the 3rd power plus c. There you go. That's it. I started whipping through that. Did I miss something?
Just the 4 on the second, on the first ln term.
Should be 4 ln.
Oh, yeah, right there. Okay, that is a 4. Okay, so that one was a 4. I just kind of got to going fast on that. Yeah, so that one's where that 4 comes from, like that. So in your final answer, you should have that thing right there. Okay, something a little different. Okay, does that look okay? Okay, well, that'll wrap us up for partial fractions. Now, don't go, because I'm going to give you a copy of your grade. Okay, and